Good day, everyone. So in this lecture, we will have a brief understanding of map projections. So this is basically conceptual understanding, and I will not detail any mathematics in this lecture. So the objective or idea of this lecture is to give you an understanding of why map projections are needed, and what are the problems with map projections, and basically how we apply these, and to what areas, and what are the precautions that you need to take while preparing maps. So this is the outline of this presentation. And first we will discuss the purpose of having map projections, why we need those maps on 2D sheets. Then we'll speak about the issues in map, for example, what are the distortions, and what is the process of making these maps. Then we will speak about some cases of projection, the different classes, the different cases, and the aspects. Then to characterize or categorize the distortions, we use T-source indicatrix. So we'll speak about what are T-source indicatrix and how they indicate the amount of distortion that takes place in the 2D projection or in the maps, projected maps. Then finally, we'll discuss about or give a description or details about the universal transverse Mercator, which is widely used in variety of purposes. So the purpose of having a map. So we know that the best representation of the Earth is on an object is basically the globe that you used to use in your school days, I think. So basically, the globe is a 3D representative of Earth. And we know that we've seen different sizes of globes, very small, tiny ones that you used to give to your friends, your teachers, to a large ones that are there in your probably in your geography classes. So maps are these globes. They are very expensive to make. They are difficult. They are cumbersome because you need to have a lot of process in preparing globes. But the problem is, even after doing all that stuff, you don't have enough detail. For example, you can see the country boundaries, but not enough detail. So if you were to discuss or show some small area on a globe, it's not really possible. But the advantage is there is no distortion in globe models. So why use maps? So let's think about that you have some event going at your home right now, and you want to give the directions of your neighborhood to people. Then would you be willing to make a gigantic size globe model and then present this to the people that you want to invite? It's not practical, right? And just imagine that you have this event at some other location, maybe next month. Then again, you have to make that gigantic map, gigantic globe for that location. So this doesn't seem practical at all. So the solution to this problem is having maps. So of course, these are 2D representations of the globe. So these are much easier to carry around or measure distances, areas, and directions. They show a lot more detail. You can blow up any area of your choice from the 2D map, and you can show much more detail, like some roads or buildings or anything, depending upon the scale of the map. And they are easier to work with. They're portable. They're cheaper. But the problem here is we get distortion. Now, distortion is necessarily not very bad because there are ways to counter it, to minimize it, although distortions are inevitable in maps. So let us first imagine that our reference globe, which represents the scaled or shrunk version of your Earth. So this Earth can either be a sphere or an ellipsoid, depending upon the choice. And usually the softwares that we use for preparing the maps, they take care of all the calculations, whether you want to choose a sphere or the ellipsoid as your reference Earth. So let us assume that we want to prepare a map at the scale of 1:100 million. And for that, we shrunk the Earth from its original scale to this scale. And this is known as the principal scale, the scale at which you want to prepare your map. So basically, the principal scale is nothing but the ratio of the radius of the reference globe to the radius of the Earth. So the easiest one, or the most simple case, is that of selecting the principal scale to be 1:100 million. But of course, when you prepare the maps in more detail, this changes. So the idea behind preparing the 2D map is to transfer all the points from the reference globe to the 2D surface, flat surface. And as you can already see here, the distances, they are no longer preserved between the points on the 2D map. So another example, classical example, is here where you have the equator and maybe some latitude here, mid-latitude here. And you will see that these are projected at the same length on the 2D map. A classical example to see how distortion works is, for example, the North Pole here is stretched out as a straight line here on the 2D map. So basically, in this process, what we are doing is we are flattening the globe, we are stretching it, we are tearing it, and we are distorting it in some areas. The classic example here is, for example, if this blue surface is the Earth, the reference globe, and we have a sheet of paper we want to project this reference globe on. And let's say if these are the 2 points that we want to project the distance between. So the actual distance on the reference globe is much larger than that on the map. This means that we are basically shrinking down this length here on the 2D map. So let's take an example of the Mercator projection. This is an example of the Mercator projection. So let's assume that we have a sheet of paper that is surrounding a wire mesh model of the globe, where these black lines, they are the graticules of the wire mesh. And we have an energy source, a light bulb, that is projecting light outside, radiating light through these graticules. And what we are trying to do is we are trying to project the shadows of these wires on the sheet of paper. So if we analyze the pattern of these shadows, the graticules, we see that the point at which the sheet of paper touches the wire mesh, that is the equator, close to the equator, we have the graticules at equal distances. But as we move forward towards the pole, either the north or the south, the distances between these latitudes, they keep on increasing, meaning there is distortion that keeps on increasing as we move away from the equator. So let's take another example where we draw a line on the equator, and from this we project on a meridian some points that are distanced equally. Now, if we were rotate it around and project these points on a sheet of paper, we see that when projecting these points on the sheet of paper, the distances, they are no longer preserved. So for example, on the reference globe, these 2 points and these 2 points are at the same distances. But on the sheet of paper, you will see that these 2 points, they have much larger distance than these 2 points. So this means that in this case, as we move from the equator to the poles, our distances, they are shrinking. So this is an example of the cylindrical equal area projection. So you can see that from the equator, as we move towards the pole, the distances between parallels, they keep on decreasing. So your latitudes, they keep on getting closer and closer as we move towards the poles. But the distances between the meridians, longitudes, they are uniform, they are constant. However, is this a good thing? No, because you see on the reference globe, all of these lines, these meridians, they converge on the North Pole and the South Pole. But in this equal area projection or the cylindrical projection, these meridians, they are always parallel. So this indicates that everything around the poles or near to the poles, it is always distorted. So let us take another example where we have equal distances when we map these points on the sheet of paper. Now, is this necessarily a good thing? Maybe or maybe not. In this case, what happens is we have the cells or the graticules at equal distances. So for example, each of these cells, they are rectangles, and you will see that the distance between the parallels now they are constant. So basically, this indicates that measuring distances along the meridians is fine because this is preserved. But we still have distortion because the meridians, they are still parallel. They do not converge on the North Pole or the South Pole. So till now what we did was we adjusted points along the meridian and we adjusted points along the parallels. But is it possible to do this for both? It's not, because you can either adjust the points along the meridian or along the parallels, but not together. So what are the different types of projection classes? So basically, there are three basic classes. One is the planar, cylindrical, and the conic projection. So by the shape of the map, you can already identify which surface was used for the map. For example, in the case of the cylindrical, in our previous examples, we described as the sheet of paper surrounding the reference globe. And this is basically the shape of the cylinder. We call these surfaces as the developable surfaces, which are used to fold the reference globe into the map. So it's easier that when your map is rectangular, you know that the developable surface was a cylinder. So in a similar way, when it is a wedge shape, you can identify the developable surface to be a cone. And when it is a circle, the developable surface is nothing but a plane. So in this case, the developable surface is touching the North Pole. And yeah. So all of this are the tangent case. So what is a tangent case? So for example, in the case of the planar projection here, you can see that the developable surface, it touches the reference globe only at one point, that is the North Pole. So basically, this surface is tangential to the reference globe at the North Pole. In case of the cylindrical surface, cylindrical developable surface, again, it is touching at the equator. It is tangential at the equator. In case of the conic, it is not tangential at the equator, but some mid-latitude. So what is the importance of this intersection or this tangent? So basically, this gives us the idea of the standard lines and the standard points. So the point or the line where the developable surface touches the reference globe is defined as the standard line and the standard points. So in this case, you will see that in the case of the planar projection, you will see that this is a North Pole, as your developable surface is touching the reference globe on the North Pole. In case of the cylindrical projection, this is a line that passes through the equator when your developable surface is tangential at the equator. In the case of the conical projection, this is some mid-latitude. So we discussed now that distortion is basically inevitable in map projections. But we need some idea of how the distortion is taking place. So what are the ways in which we can quantify or quantitate that that the distortion is, whether it's minimum or it's maximum, or whether the distortion is only in the lens or in the areas. So there is a method of doing that. It's known as the scale factor. So we analyze the scale factor and the changes it undergoes. So the scale factor is basically the ratio of the local scale on the map to the principal scale on the reference globe. So basically, we know that on the reference globe, all the locations, they have the same scale because the graticules, they are uniform. So basically, the scale for all the locations is 1:100 million as per our example. Now, where do you think will the local scale be the same as the principal scale on the 2D map? So this is along the standard line. This is why the standard lines and the standard points are very important. So along the standard line, which for example, in this case, it's the equator, that all the points will have the same scale. All the areas will have the same scale. This means that along this line, the local scale is equal to the principal scale. That indicates that scale factor is 1 throughout the equator or the standard line in this case. So what happens as we move away from the standard line? There's nothing new to define here, because you can easily visualize it, because as you move away from the equator, the distances between the parallels, they keep on increasing. So what this indicates is that the distortion is inevitable in these areas. And as you move further towards the pole, the area or the locations or the countries, they are twice as big as they should be. So basically, on the reference globe, the Greenland is shown twice as big in the map here. So if we were to calculate the scale factor in this area, so it will be 2. For example, this area is exaggerated twice as big as it should be on the reference globe. So we know that it's not possible to alleviate the issues of distortion, but are there any methods to reduce distortion? Let's see. So there's something called a secant case. Now, in case of the tangential case, we had the developable surface to be tangential to the reference globe. Now, secant case is an advancement of that case, of the tangential case, wherein now the developable surface, rather than being tangential, intersects the reference globe. So for example, in the planar projection, you will see here that the tangential surface now intersects the reference globe at 2 points now here. So this makes the standard point as a standard circle now. So all around the standard circle here, distortion is minimum. In the case, so this is another way to figure this out. So in the case of the cylinder now, the reference developable surface now intersects at 2 points, and both these 2 points they result in 2 standard lines as shown here. Now we know that the distortion, it increases as we move further from the standard lines. So we know that the scale factor is going to be more than 1 in these directions. But what about between the standard lines? So let's see. So we know that the scale factor is 1 along the standard lines. And if we were to analyze what happens between these 2 standard lines, let's take this example here again, where the blue curve here is the reference globe, and the red line here shows the developable surface. And what we are doing here is we are shrinking down this distance here on the reference globe to the map, in the map here. So basically it indicates that the scale factor now is less than 1. So this is between the 2 standard lines. The same follows for the conical projection, where we have 2 standard lines, and again this process is the same here also. So the rule of thumb to follow when preparing maps is match the region to your projection, so that you are mapping the area where distortion is minimum. So for example, if you are preparing a map for the polar regions, the azimuthal projection is ideally suitable, because in this case, along the standard lines or the standard circle here, the distortion is minimum. For the tropical regions, the cylindrical projection is better, because close to the equator, we have minimal distortion. For the temperate regions, mid-latitude region, basically, we can use the conical projection, because the standard line here is a mid-latitude rather than the equator. So till now, we discussed all our developable surface to be vertically aligned. And we saw that in the case of this configuration, the standard line is close to the equator for the cylindrical projection. And as we move towards the North Pole or the South Pole, the scale factor keeps on increasing. So this is the classical case of the normal aspect. But it is not necessary that the cylinder has to be vertically aligned. We can also have it in a transverse position, that is horizontally. And in this case now, the standard line is a meridian, along a meridian, because you see that the cylindrical surface here, the developable surface, it is tangential at the poles rather than the equator. And similar to the normal case, moving away from the standard lines in both the directions, your scale factor keeps on increasing. Now there is another way we can, project this or align the cylinder, and that is at some, predefined angle or at the angle of your choosing. And in this case, again, the standard line is at the is between the 2 points that are tangent to the that are tangential to the reference globe. So again, the scale factor, it will increase as we move away from the standard line. So this is also the case with the conical projection as well as the planar projection. So in the case of the azimuthal projection or the planar projection, we can have the normal aspect or we can have the equatorial aspect. We call it as the equatorial aspect rather than the transverse aspect, because in this case, your developable surface is touching the equator. And we can also have this oblique case where, for example, if this is suitable when you want to prepare a map for a city or a specific location where you want distortion to be very minimum. So for example, if you want to prepare a map of Delhi, then in this case, I will have this developable surface tangential at Delhi on the reference globe. So we saw that scale factor is one of the ways to quantitatively determine the distortion in the 2D map. Now there is another way in which we can do this. This method is called as the Tissot's indicatrix. So it gives us a qualitative analysis of the distortion that is taking place while transforming the 3D globe to the 2D map. So let's just take an example of Greenland. So this is on the reference globe, and you can see that the meridians, they are converging towards the North Pole. And the latitudes, they are curvilinear and parallel to each other. Now on the Mercator map, for example, you will see that these meridians, they are now parallel. And you will see that this distance here is stretched out. So we know that this distortion is taking place here. But is it a good idea to always take some country or some continent to identify how the distortion is taking place? Because this is not really very practical. So the idea behind Tissot's indicatrix is that you can develop or project very small circles, infinitely small circles on the reference globe. So on the reference globe, these are all circles. So these are infinitely small circles, but for illustration here, they are made large so that you can understand how this Tissot's indicatrices, they work. So for example, here on the reference globe, all of these are circles. But when we project it on the 2D map, they can either be circles or they can be distorted, shrunk shapes similar to ellipses. So when we see these circles on the Mercator map or the projection or the projected map, we can identify whether the map holds the properties of conformality, that is the area, the shape of the areas or countries, they are preserved, whether the areas are preserved along these Tissot's indicatrices, or whether distances are preserved. So let us take an example here where we have this Tissot's indicatrix, the infinitely small circle, and let us define the two radii here as in the north direction and the east direction as A and B. Now on the reference globe, both A and B, which represent here the scale factor, are equal to 1. And therefore the product is also 1. Now let us take an example of the cylindrical equilateral projection. So in this case, we know that along the standard line, we do not have much distortion. And as we move away from the standard line, the distortion increases. So look at how the T-source indicatrix is, it keeps on shrinking as we move away from the equator. So you can see this, there is some shrinking along the north-south direction here, and this is highly exaggerated along the near the poles in both the directions. So what happens here is that the T-source indicatrix along the poles, it keeps on shrinking in the north-south direction. So our new radii, scale factor radii, is no longer equal to that on the reference globe, but it has shrunk. And in the east-west direction, it has stretched. So that means that the scale factor now is no longer the same as on the reference globe. So the scale factor has increased in both these directions. So you can clearly see here that it's along the north direction, the scale factor, new scale factor has reduced while it has stretched out. So the scale factor now is much larger than on the reference globe. And therefore, when we take the product of the new scale factors, because there is a reduction and increase, when we multiply them, the product of the scale factors is still 1. While both of them, they are no longer equal. Basically, this indicates that this new map, it shows equal areas, but distorted shapes. So basically, this is the equal area projection with non-conformal aspects or properties. Let's take another example of the Mercator projection. So in this case, you can clearly see that the circles remain circles. So do not have to tell you that the shapes are preserved. But let's see how, let's see by example of the circles here. So as you can see that as we move towards the pole, the T-source indicatrices, they keep on increasing, but they remain circles. So basically what happens is that both A and B, they have increased now. So the scale factor has increased both in the north-south direction as well as on the east-west direction. And if you see on the map that scale factor still increased, is greater than 1 in both these directions, perpendicular directions. So if we were to identify this in terms of the new scale factors, the new scale in near the poles, both the scale factors in the north-south direction as well as in the east-west direction, they are increased by a factor delta. This could be any number depending upon how much it is blown up. So now that both of them has increased, their product is no longer equal to 1, but greater than 1. This means that this projection system is a conformal projection that preserves the shapes, but it distorts the sizes. So you do not have the same sizes, but and as well as you do not have the equal areas. So let's talk about some equidistant projection systems. So the most common one is the plate carré projection or the equirectangular distance projection, equidistant rectangular projection. So in the plate carré projection, carré is French. So the distances along the meridians, they are preserved. So when we are measuring any distance along a meridian, they have no distortion and they are the same as on the reference globe. But you can clearly see that along the parallels towards the poles, the indicatrices, they are stretched out. That means along the meridian, the scale factor is 1, but along the parallels, it is not. So another example here is, for example, these meridians, they should have been converging, like on the reference globe. But on the 2D projection, you see that they do not converge anymore. So, for example, if you were to talk about one of the parallels here, mid-latitude region here, you will see that the equator from here, reference globe, is the length of the standard line here. But if we were to project this latitude on the map here, you will see that this is also the same length as the standard line. This indicates that there will be distortion as we move away from the equator towards the poles. Let's take another example of the azimuthal equidistant projection. So this is the planar projection And you can easily see here that the standard point is on the North Pole. So along the meridians, the scale factor is 1. And as we move towards the pole, the distortion between the meridians along the latitudes, it keeps on increasing. And therefore, in these regions, the scale factor is greater than 1. So to summarize, ideally, you want to preserve the length of the lines, the direction of the lines, the size of the features, and the shape of the features. But in practice, we always need to do a trade-off. So basically, it's a compromise between preserving either or more of these properties at the expense of the others. So what is the solution to that? So one of the ways is the universal transverse Mercator. So this is basically an adaptation of the conventional Mercator projection, where we make an effort to minimize the distortion. So we know that in the case of the Mercator projection, the distortion is minimum along the standard line. In case of the transverse Mercator projection, the standard line is basically a meridian. So close to this meridian, the distortion is minimum. And so people define that this is the 6-degree wide zone across the standard line where the distortion is minimum. So this 60-degree basically defines one zone of UTM. What if we kept on rotating the cylinder to map each of the meridians, and then we assimilate these 6-degree strips into one complete map? So this is the idea behind the universal transverse Mercator. So in UTM, each of the zone is 6-degree wide, and to cover 360 degrees of the sphere, we need these 60 zones. And each of these 60 zones, they have their own central meridian. So this is the UTM zone map of the world. And you can see that it stretches from 1 to 60 zones. And along the parallels, these zones are defined with alphabets. So it's numbers along the latitudes, and its alphabets along the meridian. So for India, if you were to look into this, India is covered by 4 zones along the latitudes, 42 to 46. And, and in case of the meridian, it is covered by alphabets from S to P, P to S. So let's take another example, the coordinate systems of the UTM, because people wanted to work with a Cartesian system with UTM, because you know that in case of the geographical system, it's all the angle, the distances, and everything is measured in angles. But people wanted to use Cartesian system where we can measure distances in meters. So what they did was they defined a new coordinate system for the UTM system, projection system. So this coordinate system basically is a Cartesian grid that is mapped over the each of the UTM zones. So when we see this, visualize this, in the case of the UTM, the latitudes and the longitudes, they are equidistant. And each of the cells is basically a square. This makes measuring distances much easier in case of UTM as compared to the geographical coordinate system. So the problem with the conventional Cartesian system is that we can have points that have negative x and y values. And this makes the job of measuring distance a little bit tedious. So for example, if we have an area that extends into each of the quadrants, then some of this is positive, some of this is negative. And we want to simplify things. So what we do is, in UTM, we stay positive. This means that we shift the entire grid, we shift the XY axis, the origin of the axis, to the point here, so that our entire area is always in the positive direction. So this is the entire map of the zone, 6-degree wide zone, and we have the central meridian at the center. So the 4 quadrants in this case would appear like this, and 0, 0, the origin is shown here. So in the case of the UTM, we shift the central meridian, this y-axis, from the central meridian to the westmost edge of the UTM zone. And this makes this point here as our new origin, and this intersects the equator. Now, in case of the UTM, all we have to do is we have to define the hemisphere we are in. So it can be the north hemisphere or the south hemisphere. So in this case, in either of the cases, we are measuring distances along the direction of the north, that is from the origin towards the north direction, or from the origin towards the east direction along the equator. In the case of the southern hemisphere, however, again we need to shift the origin, because if we follow the same criteria, in this case again we have the negative easting. So we want to avoid that, and therefore for the southern hemisphere we again shift the origin to the bottom as shown here. So all we have to do is specify the hemisphere we are in, and our Cartesian grid, it works. So for further reading into all the different topics that were discussed today, I refer to you the book by Rampal and Sickle. This gives you conceptual understanding of how the different map projections work. And for more details about the variety of map projections, you can read in Kennedy and Koch. So this is basically gives you a brief overview about each of the projections within all the cases or the classes that we discussed today. And you can also follow some other books that give you a more practical aspect of using map projections. For a mathematical understanding of the transformation from the 3D reference globe to the 2D map, I think I would refer you to the book by Schneider. So this gives you all the mathematical relations, details, how the projection or mathematically is carried out. And also I would refer you to the lecture notes by Crum. And these are very comprehensive lecture notes, and they have all the step-by-step explanation mathematically of all the different types of projections. So this is all from this lecture. Thank you. And now, yeah, if you have anything to ask, yeah, I'm here for it.